Welcome back. In the last video, we began exploring Richard Byrd's 1989 paper, Algebraic Identities for Program Calculation. Byrd studies two classic problems, min-max and the maximum segment sum. In the previous episode, we focused on the fusion laws and used them to derive the alpha-beta algorithm. In this episode, we continue with the rest of the paper. Here, Byrd gives one of the most elegant program calculations in the literature, the maximum segment sum. He starts from a naive specification with cubic complexity, and through a sequence of algebraic laws, derives a linear time implementation. Let us start with the data type definition. In the previous episode, we extended the integers with both positive and negative infinity. That choice allowed us to define clean max and min operators. But for the maximum segment sum, this definition becomes a problem. We need a lawful addition operator to compute the sum of a list of numbers. And with both infinities present, addition no longer behaves like a monoid. More importantly, we do not need the minimum operator at all. So we simplify the type. We keep only negative infinity. This gives us a clean addition function, while still allowing us to define the maximum operator. The new type has just two constructors, fin for ordinary integers, and negative infinity. Below the type, we define two binary operators. The up operator returns the larger of two values, and the plus e operator defines addition that respects negative infinity. Viewers should now convince themselves that both operators form monoids. Addition on this type is a monoid, with 0 as the identity element. The max operator is also a monoid, with negative infinity as the identity. The link to the full code, including the proofs of associativity and identity, is available in the description. Let us look at three functions that are central to defining the maximum segment sum. The first is max. Given a list of numbers, it returns the maximum element. If the list is empty, it returns negative infinity. This is a left fold using the up operator with negative infinity as the seed. The second function is sum. Given a list of numbers, it returns their total. If the list is empty, it returns 0. This too is a left fold, using the plus e operator with 0 as the seed. The third function is segs. It returns all possible segments of a list. It relies on two standard list functions, inits and tails. For any list, inits returns all prefixes, and tails returns all suffixes. By mapping tails over the output of inits, we obtain every possible segment. Concatenating the result gives us a flat list of all segments of the original list. Now let us look at the maximum segment sum. We see two definitions on the screen. The first is the specification. It computes the sum of every possible segments and then takes the maximum of those sums. This definition is simple and declarative, but it runs in cubic time. Starting from this specification and using the fusion laws we saw earlier, Byrd derives the linear time implementation shown below. In the rest of the video, we will understand how this derivation works, step by step. Before we begin the derivation, let us look at a real application. You are now seeing a portion of the E.coli genome sequence taken from the National Center for Biotechnology Information. The full genome is about 4.6 million base pairs long. Genomic analysis often requires identifying AT-dense regions or GC-rich regions. AT-rich regions are stretches of DNA with a high concentration of adenine and thymine. These regions are biologically significant. For example, they help geneticists locate the origin of replication and the termination sites. The maximum segment sum calculation forms the foundational building block for the algorithms that are used to do such analysis. We can convert the problem of finding the most AT-rich region into a simple numerical sequence. Assign +1 to A and T. Assign -1 to G and C. Once we do that, the problem reduces to finding the segment with the maximum sum. Here is the core of the C++ version of the algorithm. It is the same structure we saw in Agda. We use fold left from the ranges library, and the update function is identical to the Agda definition. The link to the full C++ code, including faster parsing, and instructions for downloading the E.coli genome, is available in the description. Now let us return to the derivation. We introduce a fusion law that we did not use in the previous video. The fold-scan fusion law. On the left-hand side, we have a fold applied to the result of a scan. On the right-hand side, we collapse both operations into a single left-to-right pass. The derivation is simple, inductive proof with the base case being simple ref L. The next law is called Horner's law. This is one of the key observations in Bird's paper. We all learned Horner's rule in school as an efficient way to evaluate polynomials. Bird generalizes the idea. He shows that the same pattern works, not just for addition and multiplication, but for any pair of binary operators that distribute over each other. For this video, we specialize the law to our extended integer type, and specifically to the max and add operators. The specialized Horner's rule is shown here. On the left, we compute the maximum of the sums of all tails of a list. On the right, we have a linear implementation, a left fold on a function that adds two numbers and truncates the result to 0. The fold is seeded with 0. The proof is a simple induction. The base case is immediate. Both sides evaluate to 0. In the inductive case, we expand the definition of tails, use a helper lemma that relies on the fact that the up operator forms a monoid, and then apply the induction hypothesis to the inner list. A final helper lemma brings us to the right-hand side. On the left, we have the specification of the maximum segment sum. On the right, we have the linear implementation. The proof is a masterclass from Bird on elegant program calculation. We begin by expanding the definition of segments. Next, we apply map promotion, called concat map in the Agda standard library. We then use fold promotion to move the fold inside the map. After that, we apply map distributivity twice, which puts the expression in the right shape, to use Horner's rule. Once Horner's rule is applied, we use a theorem from the standard library to rewrite the map of a fold over a nits as a scan. Finally, we apply the fold-scan fusion law that we introduced earlier. This collapses the entire computation into a single left-to-right pass. And that completes one of the most elegant program calculations ever written. The description contains links to the full Agda development, the C++ implementation, and Jeremy Gibbons' tutorial paper on a generic formulation of the problem. Enjoy.